In previous videos, we've done DVB-S transmission to do digital amateur television with standard satellite set-top boxes. Today with a twist, to get a little more range, we're actually going to transmit in the 70cm band, and we'll be introducing a passive mixer to upconvert to the 23cm band directly at the satellite receiver itself. Don't go anywhere, you're watching Signals Everywhere. If you're interested in software-defined radio and radio communications in general, please be sure to hit the subscribe button and the bell icon so you don't miss any future content. Before we hook everything up, we want to get a good idea for how many channels we can fit in our 12 MHz of available ATV spectrum in the 70cm band, as well as figure out what frequencies we need to use to make everything work. The first one we need is our local oscillator frequency. In this case, I'm picking one of 820 MHz. This is going to let us know essentially what signal we're mixing with our 70cm amateur television signal. In this case, for channel 1, we picked a signal of 421 MHz. We'll get back to the set-top box's 10 GHz signal in a moment. With the local oscillator punched into my spreadsheet, we can now see that we have all of our channels here available. So channel 1, I'm going to transmit our signal at 421 MHz. Now when we mix that with our 820 MHz local oscillator, it's going to give us a frequency of 1.241 GHz, which is actually within the receive range of our set-top box. Now because the set-top box is going to think it has a 10 GHz local oscillator from an LNB, we're actually going to set that for 11.241 GHz. So this spreadsheet makes it nice and easy to see everything that we need here. And you can see that I've set it up with 6 channels. The reason for this is we're going to transmit at 1.5 megasymbols. It's going to make our ATV signal roughly 1.8 megahertz wide. And so because most set-top boxes will only let us go in 1 megahertz steps between channels, I did this so that way each channel is no larger than 2 megahertz wide. And I know that there's no way that any one of the 6 channels will be able to overlap with one another. Now we can finally start setting up our hardware. Now one thing I want to note is LNB power. My particular set-top box satellite receiver has the ability to turn this off. However, a lot of set-top boxes don't have this option, and it's very important that we can disable the power for the LNB. Because if you are unable to do that, and you try to attach an antenna directly to the LNB, you're going to have power running through that antenna wire at all times, and you can possibly short things out or get a shock. So in my case, or rather in your case, you can use one of these DC blocks. This one goes from 5 to 2.4 gigahertz and is perfectly suited for what we need to do here. It's just a little F connector, and then from there I've also placed a F to SMA connection so that we can connect our passive mixer. Now, a mixer is something we've discussed on the channel before, but essentially we're going to have an RF input, an IF output, as well as a local oscillator input. So we have an antenna on the RF input, and the RF IF is going to connect directly to our set-top box. So the IF is the intermediate frequency. Basically anything that gets mixed is going to come out of that port and into our satellite receiver. Now, in order to mix our 421 megahertz ATV signal into the 23cm band, we need to have an LO, or a local oscillator. So as a proof of concept, I'm using the HackRF as my local oscillator. This is going to generate my 820 megahertz signal. So we're just going to attach the output of the HackRF to the local oscillator input of the mixer that is currently attached to the satellite receiver. And if you're interested in learning a little bit more about how passive mixers work, I'll put a link in the description below to one of my previous videos on that very topic. The HackRF is probably one of the last things you would want to use as a local oscillator. However, for a quick proof of concept, this will work just fine. I'm running the Mayhem software. We're going to go ahead and run over to the transmit option here on the menu. And from transmit, we're going to head over to the microphone option. And I'm going to use the microphone to generate my signal. Essentially, we are going to set our mic frequency to transmit from the 100 megahertz that's defaulted here. We'll just wipe that out, and we're going to punch in 820 megahertz, which is what we decided to use for our local oscillator frequency. We're going to go ahead and tap the voice activation here. Voice activation is essentially going to transmit the quote-unquote microphone automatically for us when it hears any voice level detected. So we just turn the level down to 0, and you'll see the HackRF will begin to transmit for us. With all 3 of these devices set up and running with the Pluto SDR as our DVB-S transmitter, we can go ahead and move on to the next step to begin setting up the rest of the reception process. Before we set up the satellite receiver, we need to transmit with our DATV Express software and just confirm that we are transmitting at 421 MHz at 1.5 megasymbols. Over on our satellite receiver, we're going to head over to our antenna settings, and these are going to vary a little bit depending on the satellite receiver you have. The main feature we're looking at here, of course, we want to have LNB power off if it's an option, but we need to look at our LNB frequency. If you recall, back in our spreadsheet, we decided to use an LNB frequency of 10 gigahertz. We'll want to make sure that's set here, and go ahead and just turn off anything extra like the 22K tone or DISEC. With that out of the way, we're going to pull our menu back up and begin to enter our transponder frequency information. Essentially, we are going to set up this DATV channel as if it was a satellite transponder. So for the frequency, we're going to enter the same thing we had in our spreadsheet, 11.241 gigahertz. Our polarization does not matter in this case. And we're going to be using a symbol rate of 1500. And from there, we just hit OK. And once our transmitter is up and running, we should see the quality and strength meter. And I'm just going to go ahead and hit search. And it's going to tell the satellite set-top box to scan that transponder for a channel. And you can see it found a channel called the Pluto SDR. So when we back out of the menu, it will then pull up the Pluto SDR channel. And there we go. You have a quick video here of my webcam, my call signs being appended in the upper left corner. A full tutorial on how to use DATV Express will be in the description below. And there you go. There I am. So from here, we can do a little bit more exploration with this. Of course, this is being received at 1.241 gigahertz. However, we're only transmitting at 421 megahertz. So let's go behind the scenes a little bit and show you how that's actually functioning. In order to show you exactly what the satellite set-top box is seeing, I went ahead and connected the output of our mixer into a AirSpy SDR here with Spectrum Spy. And you can see here is our 421 megahertz signal being transmitted here. And once we kick on the HackRF, you can see we have a very nasty, very dirty 820 megahertz signal coming from the HackRF. And that's actually causing it to mix with our 421 megahertz signal, giving us a signal at 2.41 gigahertz over here to the right. So let's go ahead and zoom in and we can get a better look at the frequencies and the mixing that we actually have occurring within our passive mixer. So I'm first going to go ahead and we're going to move over to 1.241 gigahertz, and you can see the signal is actually pretty weak in the passive mixer. Keeping in mind we're using a rubber duck antenna for the RF input, but as I toggle the Pluto SDR transmit on and off, you can see pretty clearly we do have a QPSK carrier that is showing up in the signal here. And it really goes to show you how well these set-top box receivers are able to pull down these signals, especially when you consider that this set-top box only sent me back about $20 or so. From here, let's go ahead and move over to 421 megahertz, where we can see the input signal that our Pluto SDR is actually sending out in the 70 centimeter band for amateur television. And then from here, we'll go over to 820 megahertz, and you can see we have an extremely dirty signal coming from our HackRF as a proof of concept local oscillator. If you were going to use this full time, you definitely want a proper local oscillator, something filtered. But for proof of concept, this works pretty well, and I'm just toggling it on and off here. Moving back to the television with the set-top receiver here, I'm going to keep the 421 megahertz signal transmitting, and as you can see here, I just turned off the 820 megahertz signal that was being generated on the HackRF for our local oscillator. As I turn it back on, almost instantly our video feed comes back with a nice high, or well, rather low bit error rate. And you can see as I turn the HackRF signal source on and off, you can see as I have everything pointed at the fan here just to show that the video does freeze up when that 820 mixing signal is shut off. So here as I turn it off again, you can see that my video is pausing and I have no signal. and as soon as I turn the hack RF back on, that 421 megahertz signal is mixing with the 820 megahertz signal, and we're going to get our 23 centimeter output at 1.241 gigahertz back up and running again. So as I just toggle this back and forth, we can see pretty clearly that the mixing works pretty darn well. And just to show how well this actually works and the video quality we're able to get from this particular transceiver, I went ahead and just set up a quick little test screen, and I'm using some YouTube safe music just to give you guys a quick and easy example of how everything is coming in here. You can see that the quality and strength is kind of all over the place. I'm sure that's a mix of issues there where I have a very, very crappy antenna on the mixer for the input, as well as the fact that this is a pretty cheap receiver, but it does seem to be working pretty well. Now, of course, I do understand on the amateur radio band we're not allowed to transmit music. However, I am in the fraction of milliwatts here, and I'm not going to worry about it for the sake of this video, because it really is just a proof of concept to show you what you're able to do. I think here this twitching thing that it's doing in the EPG is just a matter of the fact that while I am setting this up to encode at 1920 by 1080, for some reason it's doing 1920 by 1088. I'm using some crappy webcam software to actually inject the video feed, and unfortunately my computer really doesn't like it. It jacks the CPU way up, and it makes it very hard for the computer to cope with any of the encoding that's going on during this process. So generally using a webcam and a microphone is going to be your best bet when you are transmitting your signal. But yeah, we're doing a pretty darn good job transmitting at 421 megahertz while actually receiving in the 23 centimeter band. That's it for today's video. I appreciate you guys hanging in there with me. I know it took a while to get this one out, but I hope you enjoyed it. Links for everything will be in the description below, including where you can buy the hardware if you want to play with this yourself, and of course links to previous videos where I showed you how to use the ATV software, and even things like decoding this in software instead of decoding with a hardware receiver. So again, I hope you guys enjoyed it. Big thanks not only to my subscribers, but all of my patrons who just make all this worthwhile. And you guys have supported me through some extremely hard times, and a lot of you guys are still there after all this time and the hiatuses that I've had, and I really appreciate it. So sincerely from the bottom of my heart, I appreciate you guys. Thank you for being there, and I hope to see you all in the next video.